All right, this is chapter 1, part 2. We're on measurement scales. The first one is nominal, and it's perhaps the simplest level. It's really categorizing data into distinct groups, but they have no ranking or ordering. Okay, so the characteristics of nominal, it's categorical data, like colors, gender, political affiliation. There's no ordering to these measurements. Red is not greater than blue and vice versa. They're mutually exclusive, which means you cannot be in two categories at the same time. You have to pick one of those, and then that's the category you're measured in. Now, what can we do with nominal data? We can calculate a mode as a central tendency. Now, remember, the mode it's the measurement that occurs most often or most frequently. And that's about all you can do as far as central tendencies. Now, we had a variable called xcat, and when we printed, these were our 10 observations. But notice this right here. It tells us the levels. So that already tells me that we use the factor function to create a factor variable, which is essentially, it's nominal, and we've told R that it is, and so it will know how to use this when we use it in functions. Now, R doesn't have a built-in function to calculate the mode of nominal data. So let's build one. So we're going to use the function in R, and this is going to be the name of my function, find mode. And so we're going to enter a categorical data set, find its unique values. We're going to tabulate, these. So we're going to find out how many, the frequency of each category. We're going to find the maximum, and then it prints it. And so if we find the mode of this variable, it's red. And if you look, there's 1, 2, 3, 4, 5 of these. There's only 1, 2, 3, 4, and 1. So it is the mode. And there's not a built-in function for R to do that. Now, ordinal scale, I actually think of it just like nominal. So it's categoricals, and you have labels for your categories, but there's a meaningful order to them. But the ordering, like the difference between categories, doesn't make sense. So the difference between low and medium and high, those don't have to be the same distance or meaning. So there's only a meaningful order. So it's essentially ordered categorical variables. So satisfied is higher than neutral, or dissatisfied is lower than neutral and lower than satisfied. Okay, there's no fixed intervals. And I think that is a mistake that's made sometimes, is that you assume there's a equal distance between dissatisfied and neutral and satisfied, but there's not. Now, the central tendencies that we can do with ordinal data is we can find the median and we can find the mode. Now, the mode is the value that occurs most in your sample, and the median is the value that at least 50% is below it and at least 50% is above it. Sometimes the median doesn't exist in these ordinal data sets, but here was our ordinal data, and there are the values, and you can tell that printed out. So we used the factor function, and this was the ordering that we specified. Now let's find the mode. This is the built-in function that we created, and it says high occurs most. So 1, 2, 3, 4, 5, 6. Clearly, there's only 10 observations, so it's the mode. Now, let's find the median. So it's the value that it has at least 50% above and at least 50% below. And again, So this is, we're putting in our data. We want to find the 0.5 percentile, which is the median. And type 1 tells us the type of data that we're using, or the type of median that we're calculating, I mean. And this is it. So there's 1, 2, 3, 4, 5, 6. So there's, more than 50% below it, and there is more than 50% less than or equal to it. And so it is the median. Now, interval scale is the next type of measurement. And then interval, of course, you think of it over an interval. So you have, it's a range of values. It's quantitative, so it's numbers. And ordering makes sense. The difference between two values, so that between any two values, if it's the same for another two values, that difference makes sense. The point that's tricky about interval scale is that there's no true 0 point. And of course, the biggest, and so that means like 0 doesn't mean the absence of something. And temperature, of course, is the quintessential example used here. If we're measuring temperatures in Celsius, the 0 value doesn't mean lack of temperature, right? It's just 0 on our scale. But the difference between two values, the difference between 20 and 30 it has the same effect as between 30 and 40. The difference between two values, right? It's ranked. It's meaningful. The intervals between differences make sense. There's no true 0. And this right here is actually often messed up in interval data. So addition and subtraction makes sense and it's valid, but multiplication and division are not meaningful. Is 40 degrees Celsius twice the temperature as 20 degrees Celsius? If we convert that to Fahrenheit, then it's not. And so you just have to be careful. Now, a ratio scale is the most flexible. It's the highest level. It's just like interval scale, except for the 0 is a true 0 point. It means the lack of something. So the characteristics is that there is a true 0. It represents nothing. Like 0 weight means no weight. The equal interval, so the difference between points makes sense. If the difference between several points is all the same, it means something. 10 centimeters to 20 is the same as 20 to 30. The mathematical operations that make sense in ratio scale data, addition, subtraction, multiplication, division, they're all equal. Okay. And in ratio data, ratio comparisons mean something, which means proportions make sense. And so 20 kilograms is twice as heavy as 10. And so it makes sense to compare ratios. So statistical inference it's a way to make guesses about your population based upon your sample data. So we're going to look at the types of sampling and statistical inference. Okay. So first, it's simple random sample, and that means that if we're going to draw a sample size n from a population of capital N, it means that every single sample of size little n has equal probability of being drawn, so it has the same chance. So that's simple random sampling. And you can do it with and without replacement. So if we're rolling a 6-sided die 5 times, we use that same die 5 times. So we're sampling it. using it again, putting it back, sampling it. And so that sampling so you can have simple random sampling with replacement or without replacement. So if we're playing poker and we randomly shuffle a deck and draw 5 cards, that we're taking a card and keeping it. We're not putting it back in the deck, and then we're taking another one, and we do it 5 times. But the probability of those 5 cards is the same probability as any other set of 5 cards. Simple random sampling. Systematic sampling, it's really we're taking observations at a interval, or like a fixed interval, and I'll show you what that means. So we're taking like every kth element or every nth element in a sample, and the criteria, you have to randomly pick a starting point, and then you keep every nth observation in your sample, or every kth observation. So it has to be a regular interval. So we're going to keep the nth element from the population, and then, but we need a random starting point. This first starting point is random, and then we collect the kth, we observe more observations, but when we get to the kth one, we keep it. And then when we get to the next kth observation, we keep it, and the next. Okay. This is often easier to implement because you don't have to give every observation of population a number that we randomly choose from. We just randomly pick a starting point, and then we collect every k observations into our sample. It can be a pretty representative sample, right? Because we're spreading it out throughout time, in a sense, and which we think may represent the population better. And then stratified random sampling is where we divide the population into distinct groups, often called strata, right? One of the strata is called a stratum. And then we draw from each stratum to ensure that we get representation across the different groups. And this makes sense. If we're studying a new medication that we want to be, to give to every age group, and if we take a random sample, we may not get the elderly patients or the very young patients in our sample. And so when we collect data, can we extrapolate to those groups? I don't know. So it would make sense to, group patients into, say every decade, and then within those decades, sample so many subjects. So we have each, we have the, every age group represented within our sample. So we divide the population into strata, or relevant, characteristics, income, age, education level, and it just really ensures that we have proportional representation, in our sample. Now, it can reduce the sampling biases, accounting for all the subgroups, and it can improve precision, over random sampling, simple random sampling. Convenient sampling, and in clinical trials, this is almost always the case that I've experienced. It's a convenient sampling. So it's a non-probabilistic method. You wait for the next patient to come into your clinic, and then you recruit them to be in your study, and but we introduce a randomness by randomly assigning them to a treatment. But it's a convenient sampling. It's often used for exploratory research, but it can introduce biases. So you have to be, you have to think about what your convenience sampling is, potential bias. So the scientific method, and then of course design of experiments. The scientific method, it's really a systematic approach to answer your question, right? So first of all, we're going to identify the problem. We're going to formulate a hypothesis. We're going to conduct the experiment, or design and conduct. We're going to collect data and analyze, and then we're going to draw our conclusions. And then we want to be very careful, document everything. We want to be able for someone to repeat the experiment. So replication is important, peer review is important. Now, design of experiments, DOE, it's a very structured way of conducting experiments. And in clinical trial research, in the later phases, while it is, this is an experiment that we're designing, it's not the typical way that I think of design of experiments, but it is, and we'll get to this. We'll do a chapter on design of experiments, and I'll kind of give you the relationship to like a clinical study. But there's randomness, and that ensures unbiased selection. I think that a lot of times in books, like if you're taking a class, they say, here's your data, analyze it, and it's from a designed experiment. But you don't think about how the data were randomized into those different treatment arms. Or if there's a blocking variable, how does that affect randomization? And we're going to try to discuss all of the little aspects of randomization and how the data is collected, and not just give you, here's the data, analyze it. Control groups are very important to compare against. Sometimes a control group or placebo group's unethical. Like it'd be unethical to take someone off their current medication or the standard of care and put them on a sugar pill, to compare against your new treatment. So your new treatment has to be compared against the standard of care, but that standard of care would be the control group. Factor designs, of course, ways to study multivariables at the same time. Computers. Everything's done in computers nowadays. Nothing's done by hand. Although you collect the data by hand, and then you enter it into a computer or a database to be analyzed. But it's the only way to go, from data management to processing to modeling to visualization. Everything is done on a computer. And I really think that in most of the advanced statistical software packages, if you can do it in one, you can do it in another package. I think they're all pretty powerful. They all have their pluses and minuses. But we are going to use the R statistical software package in here. But Python is another common one. We have R. SAS. So I used these for almost 4 decades. And SPSS is another one, Stata. While it's not, I don't consider it statistical software package, but software, machine learning, AI type things. That's gonna be the wave of the future, I think. Okay, so let's stop here because this is chapter 2, and that's it. See you in the next one.